Good afternoon and welcome to this tribology webinar coming from the National Physical Laboratory. My name is Timothy Camps and I'm a senior scientist here at the National Physical Laboratory, and today we're going to be talking about evaluating performance and lifetime of advanced materials using precision tribology testing. So just to start with, I thought we'd talk about the motivation for the webinar and what we're looking to do. And the main thing here is explaining how tribological measurements can add value to business, both at the R&D stage, but also the commissioning of product, and also looking at products moving into new markets. So the presentation will start off by explaining a little bit of background about the National Physical Laboratory, background about tribology and its relationship with the International System of Units. We'll look at some fundamentals around tribology testing, and then two case studies where we've generated value based on the ability to differentiate between different materials solutions. One of them will be focused on water droplet erosion damage, and the other will look at sliding wear with in situ wear mechanism classification using some machine learning tools. So the National Physical Laboratory is the UK's national metrology institute and was founded in 1900. It's a public corporation owned by the Department for Science, Innovation and Technology, and the main site is based in Teddington in West London, with other locations in Strathclyde, Surrey, Cambridge, Huddersfield and Solihull. The strategic partners include the Department for Science, Innovation and Technology, the University of Surrey and the University of Strathclyde, and there are over 800 scientists with a breadth and depth of metrology expertise working at these sites. So I look after NPL's tribology measurement capability, and tribology is the quantification of friction and wear to evaluate performance, but also to assure lifetime of tribological components. When we think about evaluating performance, we're looking at the efficiency of surfaces that are experiencing relative motion. And when we're thinking about assuring lifetime, we're looking at whether or not those parts are going to meet the guaranteed lifetime of the product. Tribology really is a systems engineering discipline that looks at application-based solutions for complex systems, and that's substantiated by measurement science. So the three main areas of tribology are friction, wear, and lubrication. And inside each of these areas, there are different classifications of mechanism and different types of lubrication that can occur. On the right-hand side, I've got two examples of tribology testing. The top right is a solid particle erosion experiment, and at the bottom right, we've got water droplet erosion. So while the tribologists might seek to understand what's going on in these environments, they need the assistance of other scientists who can help them with specific analytical techniques in order to understand what's going on at the interface. And at NPL, I'm fortunate to be able to work with colleagues who are material scientists, chemists, surface scientists, and physicists who can all provide me with advanced analytical techniques to examine the surfaces of components that have been subjected to tribology tests. So really, when we think about tribology, it's application-based solutions that's substantiated by interdisciplinary science. As I mentioned earlier, NPL is the National Metrology Institute for the UK, and it's interesting to think about how tribological measurements map onto the International System of Units, the SI. If we consider a sliding contact, such as the one that would be produced by the equipment on the right-hand side, this is a reciprocating sliding tribometer where the sample held in the upper part is moved and the sample at the bottom is held stationary. We might think about the measurements we can make to evaluate the damage that's occurring due to sliding. And the first might be mass loss, to measure the mass before and after the experiment and see how much material is removed. In contacts that are operating in ultra mild and mild wear, this mass loss can be very, very small, particularly in relation to how the mass of the overall sample. And in these situations, measuring mass loss can be quite a difficult thing to do with suitable precision to actually achieve differentiation. And in these instances, Scientists will be interested in measuring topographical changes occurring on the sample surfaces. This might be change in roughness or specific bearing area parameters that define functional properties of the surface. And we use that, we measure those dimensional changes using instruments that realize the meter. Both of these two changes that we're measuring occur at a rate, and so we think about the unit of time and measuring rate of change in the second. At the sliding interface, where we have contacting asperities in the case of dry sliding or boundary lubrication, as you can see by the schematic at the bottom right, we might also be interested in the rate of reaction and measuring the mass of products that are produced, and so we'd be interested in the mole, and also the temperatures that are derived at these high contact pressures between the asperities. So we've got the Kelvin. Two SI units that are often not immediately associated with tribology experiments are the candela and the ampere. But some surfaces emit light, and we might be looking at measuring triboluminescence of the candela, or we might be interested in flow of electrons, particularly with the electrification of machines such as electric vehicles. And in these situations, we'd be interested in measuring the flow of electrons. It's interesting to pause and think that actually when we're measuring forces that are applied on tribological contacting surfaces, we're measuring them as a force, as newtons, and in the SI that's kilogram meter per second squared. More information about the SI can be found at the link at the bottom left of the slide. So before we think about designing a tribology experiment, we have to understand what the motivation of doing that is. And it's mostly to answer this question that's at the top of the slide, which is, can I have any confidence that laboratory tests will correlate with real-world surface performance? And there are three steps that we take to ensure that what we do in the laboratory can be read across into the operating environment. The first one is to actually understand how the surfaces that are experiencing relative motion interact with each other. So this is analysing the complex assembly. Quite often there may be secondary motions that are occurring superimposed on top of the primary motion, and these may actually be the cause of the failure or unexpected lifetime of a component. The second part is to identify the rate-limiting interfacial interaction. And when we look at this, we're looking at the condition where the power that we're dissipating in that contact is beyond the wear mechanism that we're expecting it to operate in, such as the transition from mild abrasive wear to adhesive wear. The third step is the design of the laboratory experiment to make sure that we're producing the same wear mechanism and failure modes as seen in service. Sometimes the equipment that we use in the lab doesn't look like it's replicating the environment that's seen in service. However, careful consideration is taken to match the contact kinematics and dissipated power to produce the same wear mechanism. So when we go from a large assembly down to a standard benchtop test, each step that we take away from the full assembly, maybe going to a sub-assembly, then using component parts, and then moving on to standard coupon tests, we increase the ease of instrumentation, and that allows us to increase the precision and accuracy of the measurements that we make. We increase the control that we have, so distribution of results that appears to be attributed to random error can be reduced because the input variables can be more tightly controlled. But we increase the amount of abstraction from the real world service to the benchtop test, and we have to be careful that as we reduce the number of input variables for the experiment, that we don't actually remove the one that's causing the failure or the unexpected behavior. Of course, moving from a full assembly down to a benchtop standard test, we decrease the cost and decrease the time of instrumentation and experiments. At MPL, the rigs that we use actual parts and geometries with bespoke test methods, although we also do benchtop standard coupon tests as well. While standard tests are useful for initial ranking during material development R&D style tests, bespoke engineering solutions enable specific ranking which correlate with real-world service performance and can be therefore used in design and also in remedial work. It's worth pausing at this point to consider what the difference between a friction or a wear test is. And as you'll see by the images on the right-hand side of this slide, the images are identical. There sometimes cannot appear immediately a difference between a friction test and a wear test. Indeed, many tests that produce friction also produced wear. However, the main difference is associated with what the loading methodology or the input variable methodology to precipitate failure is. Frequently with friction tests, the objective is to produce mild or ultra-mild wear, and in doing this, produce data for numerical models that allow friction loss and efficiency calculations. When we look at wear tests, where we're looking to assure lifetime, what we're doing in this case is moving a contact to the maximum power that can be dissipated while the wear mechanism is representative that of the normal operating condition, i.e. the maximum wear rate without transitioning to a different wear mechanism. And this is quite a challenging experiment to do because there can be cumulative effects, heat dissipation in the contact that can have quite a long time base to them. And so sometimes unexpected failures occur due to wear tests that have been artificially accelerated above the threshold at which they exhibit the same failure mode. Because wear tests often look at bistable systems where a contact may be operating in a steady state, it's important to be able to understand the operation conditions of the contacts that allow successful operations in the wear mechanism for which the wear mechanism has been designed. So friction and wear are system responses which require experimental quantification, and this enables systems to be optimized and failure to be avoided. Word here about standard and bespoke wear test methods. So it's very useful to use standard tests when we need to compare data to previous data that's been obtained under the same conditions. And also when we need to establish credibility of results in terms of adherence to consensus practices or specifications. And this is particularly the case if the purpose of the test is to validate a new coating or lubricant solution. If the standard meets the purpose of the wear test and it simulates the end application correctly, then it's really good to be able to use a standard test method. However, standard test methods can't be used if the application conditions differ significantly from the standard, as often the ranking of materials will differ from that seen in service. And it's really important if the test method, even if it seems appropriate, if it doesn't produce the kind of wear or surface damage that's seen in service, then it probably isn't the right method to evaluate the material. So some examples of when we might use a standard test against a bespoke test. So if we're looking to screen friction and wear performance of new products, we might look to use a standard test in a coupon level or benchtop apparatus. If we're looking at the application of specific friction and wear application, then we'll look to use a bespoke test at coupon level. If we've got a production item that's not meeting the design life, then we'll again use a bespoke test method. And the same again if we've got a production item that we want to use in a new usage case, perhaps in a different environment with a different process fluid, or in a different environment experiencing different vibration inputs. So as I said before, at MPL, we look at using bespoke test methods, using coupons or real parts and subassembly testing. And we have a particular focus on in situ friction and wear measurements for high value testing. I'll talk a little bit more about this later. Essentially, what we're looking to do is reduce the number of physical tests while increasing the amount of understanding around the wear mechanisms. The tribology research at MPL sits inside the Advanced Engineering Materials Group, and we're fortunate to be able to collaborate with scientists across the group to provide us with analysis of the worn surfaces, our surface analytical, our surface technology group, which can provide surface analytical techniques, and our dimensional metrology group, which support us with surface topography characterization. So I've got two case studies now to look at how the advanced test methodologies that we've developed at MPL can add value by informing business decisions and design decisions around material selection for solving tribological challenges. So this first case study is looking at water droplet erosion, and in this particular case, we'd be looking at gas turbine, but equally the test apparatus that we're looking at is suitable for wind turbines. So here I've got a picture of two different wind farms, one in the Netherlands and one in Scotland. One looking slightly sunnier than the other situation, but water droplet erosion is a big problem for wind turbines on the leading edge. The tip speeds can exceed 90 meters a second, and the environments in which the wind turbines are often mean that they experience quite a lot of rainfall. And the cumulative damage of the water droplets on the surface of these blades has a really big detrimental effect to the efficiency of the turbine, but also can result in catastrophic mechanical failure of the blades. So on this side, we can see the different environments in which water droplet erosion might be causing damage. So we've got steam turbines, gas turbines, wind turbines, nuclear power plants, aircraft engine, and leading edge of airfoil surfaces. And you see that there's a variety of speeds that can be run at, and there's also a variety of droplet sizes in the different environmental conditions. And the mechanism of damage of water droplet erosion is laid out on the right-hand side. We've got deformation that's caused by the droplet impacts, stress and shock waves that reflect through the material, resulting in fatigue. And then as the droplet collapses, the water jets out sideways, and it's called lateral jetting. And this can have a big impact on how materials wear if they have surface topography of an order which will interfere with the lateral jetting. And for some materials, mechanical recovery, so viscous elastic materials, it's important to consider what the impact rate is and whether the material can elastically recover in between impacts. So this is the water droplet erosion test system at the National Physical Laboratory. It's a horizontal axis rotating arm rig. You can see an image of it in the center of the slide. This arm takes a sample at each end. So it tests two balanced samples at any time, and it rotates clockwise. As the arm rotates, it passes a jet of single droplets, which are traveling into the chamber. The chamber is evacuated to allow us to achieve high speeds of up to 500 meters a second. And we can achieve different droplet sizes by varying the needle from which the water droplets emerge. And we can achieve droplets from about 300 microns up to 2 millimeters in diameter. For every test that we run, we characterize the droplet stream using a technique called particle image velocimetry. And we do this so that we can work out what the impact energy is, and with the impact rate, work out what the dissipated energy into the contact has been. In the center of the slide at the bottom, we can see a histogram of diameters against count for a particular nozzle. And the sort of image that we analyze in order to produce this is shown on the left-hand side. Because our rig is a rotating arm rig, it offers the ability to accelerate the testing of samples by over 150 times. And because of this, if we want to test in quite mild conditions, we need very precise timing of the droplet stream. And what you can see on the right-hand side is a video of the droplet stream emerging into the test chamber and being controlled by a sluice gate. The first time you saw it was at real speed, and the second time was at 30 times slower than real life. So here's a still image of that water droplet stream emerging into the chamber in front of the test sample, which is the light grey rectangle in the arm in the center of the image. This slide shows characteristic damage, or quite typical damage, for hardened steel subjected to water droplet erosion. In this particular example, the droplet size was about 350 microns. And because of the size of these droplets, there are actually 4 droplets that impact on the sample with each revolution. At the bottom left, you can see a characteristic curve for a sample that's been exposed to water droplet impingement. This starts off with a period of no mass loss. This is the incubation period, where crack networks and stresses are formed inside the material before we reach a period of maximum erosion. Shortly after that, we reach a period of steady state condition. And this mechanism, or this graph and the identification of these 3 regions, are where this test allows differentiation between different materials. So on the left-hand side of this slide here, we can see hardened steel in the uncoated and coated condition with various coatings being tested. It's clear to see that the system is able to differentiate between the different coatings. The black is the uncoated and the other colors of various coatings. But more than this, what we can see is that if we were needed to make a decision based on the lifetime or and the cost of maintenance, we can optimize the lifetime of the part based on these factors. It's important to also look at the effect of surface finish as well as the effect of coatings. And on the right-hand side of the slide, we can see results for a smooth and a ground hardened steel surface. So the green line is the smooth finish, and the red and the black are with the ground finish. And what we can see is that although the incubation period doesn't actually change very much in length, when we reach that period of maximum erosion, it does actually take a while for the smooth finish to achieve the same rate of mass loss. So in systems where it may be acceptable to have a mass loss after incubation before the part needs to be exchanged or serviced, it may be sufficient just to change the surface finish of rather than use a coating. And again, this comes down to what the acceptance limit is in the specific application, and also the cost-benefit analysis around the time interval on the servicing of these parts. So subsequent to testing, we can then look at the mechanisms that are occurring on the surface with different surface analytical techniques. The ones that are shown here are actually ones that we have inside the Advanced Engineering Materials group. Here we're using 3D optical microscopy. So this is using a variable plane 3D optical microscope to evaluate the surface topography of the area that's been subjected to water droplet erosion. We can make volume measurements and identify features. And you can see the blue circle identifying a region on the 3D images at the bottom left of the slide, with the scanning electron microscopy image on the right-hand side of the slide. This scanning electron image, or scanning electron microscope, also had the ability to use EDX, energy dispersive X-ray spectroscopy, to identify elements on the surface. And in this case, we were looking at oxidation that's been caused by the extremely high strain on the sample due to the lateral jetting as the water droplet collapses. This is possibly quite a straightforward example, but explains or demonstrates the analytical capability that can be used to understand the wear mechanisms that are going on the surface, particularly the transitions between the different rates of wear once erosion has started to occur. The second case study is looking at sliding wear, and in tribology testing using a staple of tribology testing, and that is a pin-on-disc machine or a ball-on-disc machine. And in this example, we'll be looking at the application of machine vision with machine learning and real-time wear mechanism classification in order to offer a high-value testing methodology. So the motivation for the development of this capability was all around just trying to reduce the amount of resource that was required to evaluate a new coating or lubricant, while at the same time gaining a more in-depth and detailed understanding of the wear mechanism and the transition points in the wear map for that coating or lubricant. So a conventional methodology would be to perform many tests to evaluate this performance. And of course, the validity of that test is determined by the accuracy and precision of the measurement of friction and wear, and also sliding speed and applied load, which is highlighting the fact that the test methods need to have good traceability back to the SI. An R&D program to evaluate a coating system or lubricant is conventionally very expensive and time-consuming. To reduce the number of tests. This is achieved by quantifying wear mechanisms through analysis of real-time in situ friction and wear measurements. Eventually, we look at a wear scar on the surface under an optical microscope, and experienced scientists will classify the wear mechanisms that's going on during the experiment and make inferences on quite long time bases. We're looking at friction signals. So it may be looking at the characteristic behavior of the friction force over tens of minutes or even hours, and then to look in closer detail to look at highly localized transients and try and infer points in the experiment where the mechanisms changed. And then a repeat test will be run, and the test will be stopped at a condition that meets that criteria, and the surface is evaluated to try and understand that transition. This is after the fact analysis is quite time consuming, but it also involves quite a lot of trial and error, as stopping an experiment that's in motion at a very precise point using analysis after the fact can be quite challenging. So the motivation here was to integrate machine learning into the digital test control such that machine vision could be used to evaluate wear mechanisms in real time. And here I've got a graphic to try and explain that. So conventionally, once the interface has been analysed to extract the contact kinematics, would then look to match that in the tribometer. So typical input variables might be velocity, global temperature of the contact, might be the load, and also the surface topography of the contacts. And then we might be looking to set the duration either as a cumulative energy dissipation duration. So this might be realized as a sliding distance or just as a time duration. Or we might be setting a limit on the threshold for friction or the threshold for wear measured in situ. And there are various techniques for this, both contact and non-contact in 3D and 2D for wear measurements. And then after the experiment's run, we'll be looking at surface topography characterization, microscopy, and also chemical analysis. But the change in the methodology says, well, actually, if we know which wear mechanism we'd like to reproduce, say a transition from adhesive wear from abrasive wear to adhesive wear, we may be able to define that or identify that change by looking at images that have been taken by a microscope. And when we do that, essentially we can start at the other end and we can say to our tribometer, instead of running for a fixed duration or until a fixed friction threshold, we can say run until you see evidence of adhesive wear occurring on the surface of the contact, and then stop the experiment. And in this way, we can dramatically reduce the number of tests that we need to do in order to precipitate the failure mode of interest for the study. So this is implemented at MPL using our unidirectional sliding tribometer or pin-on-disc test system. This consists of a disc that rotates underneath a pin that can be seen on the two images on the right-hand side. And as this disc rotates, it passes underneath various sensors and cameras, and these are all, and the phase angle of all of these are indexed, which allows the data to be all collapsed down so that the friction at a specific location can be seen with the 3D information and the optical intensity image of that location and various other sensors as well. This information is continuously streamed to the disk, and that effectively means that this arc of the wear track that occurs around the disk as actually manifested as a rectangle, and the image at the bottom left shows how the camera systems, which are both line scan cameras, acquire data as the disk rotates, and this is saved as a rectangular image. This system has been successfully used for clean lubricants, and we have we programmatically account for the refractive index of both the 3D probe, which is a multi-point chromatic aberration line scan probe, and the line scan camera, which is a intensity camera, light intensity camera. And we can focus this through the lubricant film and image the wear track underneath the lubricant film. So if we're looking at the formation of an oxide film, for example, we can measure that. And this multi-point chromatic aberration probe has a resolution that allows us to see very thin films. We can also look at tests on coatings, observing breakdown and delamination of coatings. So what does this look like? Well, here's a couple of photographs. In these photographs, the disc that's being tested is pink, and the ball holder is labelled there. It's the slightly yellowy goldy colour item. And you can see the objective lenses for the two camera systems labelled on the left and the right, the line scan and the multi-point chromatic aberration probe. So for our real-time classifier to work, we clearly had to create a library of images that had been pre-classified, showing different types of wear mechanism, so that we could train our model. And the model that was chosen was a convoluted neural network, and we've called this classifier WM classifier, the wear mechanism classifier. We actually produced a very large data set, over 10,000 images, and the images were classified by a number of scientists into 9 different wear mechanism classifications. In this presentation, I'll just look at 4 classifications: abrasion, adhesion, abrasion and adhesion, cracks, and abrasion. On the right-hand side, you can see an example of abrasion, class 0. This was for silicon nitride coating. And at the bottom, we can see a chromium aluminium nitride coating. So the way the system works is that as the disk rotates under the camera system captures an image. It does this every 5 seconds, and that relates to 30 degrees of the disk that rotates underneath the camera system. And then we save that image and pass it into a virtual Python environment inside Anaconda. And then we load this, having previously loaded the neural network model into memory, and that allows us to classify the image in under half a second. With recent optimizations, we can do this in about in about a quarter of a second. And that then allows us to make machine actionable measurements. So the model returns the classification of the wear mechanism. It returns the probability that the image has been classified in that class. And then it allows us to make a couple of actions based on that classification. So, for example, we can run a load ramp test until we see the transition between 2 wear mechanisms, in this case between abrasion and adhesion. So we can have a very small load increment with a time period. We can slide over a fixed distance, and we can keep asking the system to evaluate the wear mechanism. And every time that we've reached the end of our time increment and we haven't seen the transition that we're expecting from abrasion to adhesion, we can then increment the load, and that allows a fully automated experiment where we can move around until the failure is just about to occur. At this point, we can decide what we'd like to do, whether we want to fix the load and run the test just at the point of the wear mechanism transition, or whether in fact we actually want to stop the test and terminate it right as the transition's beginning to occur, and then evaluate the surface using ex situ analytical techniques. This video shows a typical example of the type of information that can be obtained by the system. This is a chromium aluminium nitride coating on an ASP23 disk, having had a silicon nitride ball slid against it. And each of the images that you're seeing is after each successive pass of the ball on the disk. And just then the coating failed. That was the bright diagonal line that formed on the surface. So as the video played, you saw the formation and removal of silicon nitride film on the surface. You can see it growing to a critical thickness. You can see it being removed from the surface and then it growing again, and the change in the wear track width as that silicon nitride ball wears a flat on the surface. What's quite interesting to note is that once the coating fails, the recess that's left in the surface very quickly fills up with debris that's formed from the sliding contact. And when we look at the friction signal that's been spatially resolved against this, what we notice is that the transient friction signal only exists for a very short number of passes after the initial failure of the coating. And this makes it very difficult to identify using conventional temporal techniques where we're acquiring the data without any, makes it very difficult to identify that the change in friction signal that we've seen is actually attributed to the removal of the coating. Yet when we use a technique where we've recorded the images and the friction signal in a way that we can rewind the data and look back at it, we can actually identify this location on the disk and see that the failure has occurred there and what the friction response is. And in some cases, it may not be of interest that the coatings failed in such a localized way, although it may be an indicator that it's about to wear catastrophically and give occasion to take the system offline. And in fact, that's what happened in this case. A couple of passes later, the coating began to delaminate from the ASP23 substrate and was peeled off from the surface, resulting in a very large amount of the coating becoming liberated. An example of the use case for this system is shown on this slide for a ceramic contact. So this is an alumina disc with an 52-100 ball being slid against it. So a bearing steel ball. And what we're looking at here is that in the early parts of the test, we had some mild abrasion occurring on the surface, and this developed into having some cracking. And in the condition that this analysis was run in, what we were looking at was free running the acquisition around the disk and seeing what the probability was that we had abrasion on the disk surface or abrasion and cracking. And you can see after the test initially started off being classified as abrasion, the probability that we saw abrasion and cracking on the disk increased from the interval 50 through to interval 250 until the whole disk was covered in abrasion and cracking. And this gives us a way of capturing the transition from just abrasion to abrasion and cracking, but also looking at how that damage propagates around the wear track. One of the other sensing technologies that we've integrated into this pin-on-disc test system is Raman spectroscopy. In this case, we've got two steel contacts, 52-100 ball bearing sliding against an ASP23 disc, and what we're looking at is the formation of iron oxide in particular. We're interested in how fast it takes for the formation of the oxide film and how tenacious that oxide film was. So there's a graph here at the bottom right, and what we can see is successive spectra, and you can see that actually the Fe2O3 peak reappeared after we'd removed it really quite quickly, and then we can see the saturation of that. So this is a measurement capability that we're developing at the moment, understanding how the system works in real time. But there is a clear advantage to being able to identify chemical species during the sliding experiment. And this year, this capability is being developed to work in the presence of lubricant, both the Raman and the Vision system, which has been already proven to work in submerged conditions. Okay, so this is my last slide, the summary slide. And hopefully with these two case studies, but also with the explanation of tribology test methodology design, it's clear to see how laboratory experiments offer increased repeatability, sensitivity, and precision, which enable quantitative evaluation of tribology systems, which quantify performance and assure lifetime. So quantifying performance, giving us our measure of efficiency, and assuring lifetime is giving us our understanding of how long the product's going to last for. As I said at the beginning, it is really important to correctly identify and characterize the rate-limiting tribological contact and select and design a successful test methodology that reproduces the failure that's seen in service. And depending on what application this is for, consider whether a standard test method is appropriate or whether a bespoke method is required. Benchtop tests that correlate with in-service performance are used to solve industrial tribological challenges without the expense of full-scale or sub-assembly testing, and they allow a range of in-situ measurement technologies to be used to understand the wear mechanisms that are occurring. As we can see, they offer the ability to put in advanced techniques using machine learning and machine vision in order to drastically reduce the number of experiments that are required to characterize the friction and wear performance of new materials and lubricants. Using bespoke test methods offers high-value empirical understanding of the tribological contact, and this can either be used for the R&D or in the design process, or indeed if there's unexpected behaviour for parts in service. Great. Well, thanks very much for attending this webinar this afternoon. I'm now going to have a look in the Q&A section. So if you'd like to ask a question, please put it in the chat now. So there's a question here that says, I have an application that I'd like to measure sliding friction, but it's at a much smaller scale than the equipment shown in the presentation. Do you have suitable equipment for this? Yes, one of our tribometers that we have, the MPL micro tribometer, sort of does what it says on the tin. It's actually a tribometer that fits inside a scanning electron microscope, and we can use various end effectors with very small radii down to 1 micron and smaller to perform sliding friction and wear tests on in situ in the SEM, and this gives us the ability to take high resolution images and understand wear mechanisms in greater detail. Another question about machine vision. The approach you've taken be used on other equipment such as manufacturing environment. Yeah, so what I didn't show in this presentation was that in order to create the data set that we needed with all the metadata tags for the images in order to train the neural network, we created a set of software that allowed us to actually curate this data and allowed the scientists to efficiently add the metadata to those data sets in order that they could then be used to train and also to validate the neural network that was developed. And this system, or the software that was designed for this, was deliberately done that it could be used to manipulate and curate data sets coming from different machines. So as long as the equipment is capable of having an encoder fitted in order to get the spatial resolution, both the imaging system and the subsequent data processing for the neural network could be implemented. And if there are no more questions, then we might have reached the end. Oh, okay, yes. So the question is, you mentioned solid particle erosion at the beginning of the talk. Can you expand on the capability in this area? So yeah, so on the slide you can see here at the top right we've got solid particle erosion. This is gas-borne solid particle erosion, and we have two pieces of equipment at MPL that can do this. One of them at high temperature and high speed, and one of them at room temperature and slightly slower speed. So slightly slower speeds up to sort of 90 meters a second, higher speeds up to 220 to 50 meters a second, and high temperature up to 800 degrees. The high temperature capability also has in situ mass loss, and this allows for high throughput, high temperature testing, as conventional solid particle erosion done at elevated temperature requires the samples to be cooled down in between each weighing interval. Whereas having the system in situ allows us to keep the sample and test rig at temperature and make the measurement, which offers a considerable time saving. Again, offer part of that approach of offering high value testing at MPL. Another look in the Q&A, and if there are no more questions, then all that's left for me to do is to thank you very much for attending this webinar on tribology at the National Physical Laboratory this afternoon. Thanks very much.